About 6, Don Landry is 6 yards away from his 6th Super Bowl. And of course, for the upstart 49ers, they're 6 yards away from Pontiac. 3rd and 3.
The right side, possibly.
Montana looking, throwing in the end zone.
Hi, I'm Sam. And I'm Dove. I'm Jake. And I'm Andrew. And this is Project Databall.
Databall is a predictive sports analytics model for the NFL. Statistical analysis has become increasingly important to the game of football over the last few years. It provides feedback to those who coach and play the game, fuels sports journalism, and of course, reels in a ton of cash in the gambling industry. Our model is one integrated predictive system. Starting with our data source, profootballapi.com, we execute API calls using PHP scripts, which return the data in JSON format. We then parse that JSON data and create a MySQL database in which we store the data. We then input the data into a statistical programming environment called R, in which we can analyze the data and identify key performance metrics. Using that analysis, we can then form our predictive model. Here's an example of some of our code. In this API call, we create a URL based on the parameters of the data we want to call. In this case, we want all New England Patriots games from the month of October. We then execute this URL to get an array of data. Next, we connect to our MySQL server and create a database in which to store the data. We then create a table within our database, adding a field to hold the values from each column of the JSON array. Finally, we parse the JSON data, add it to our database, and then close the connection to the MySQL server. This sequence of code transformed our data from raw JSON format, in which it's hard to analyze, to a neat, orderly MySQL database table. Once we have consolidated our raw data in MySQL, we can then import this data into the R programming environment for manipulation and statistical analysis. Using the R MySQL package, we can first connect to our database and then fetch all the data from the seasons we want to analyze. In this case, we're looking at years 2011 through 2015. Once we have fetched those tables, we can consolidate them into one data frame and then save this data frame into our working directory. At this point, our dataset is only raw in-game data. We need to manipulate this such that we have data that reflects a team's performance before the actual matchup occurs. Therefore, we've written a few functions to show a team's form before a game. By looping through our data, we can assemble what we call backward selection stats, which are statistics that show a team's performance leading up to a certain matchup. This kind of statistic is the foundation of our predictive model, because an in-game statistic, like how many first downs a team got in a matchup, is not helpful to predict the outcome of the game because this data is not available before the given matchup. Using 10 in-game stats, such as home first downs, home points scored, away first downs, away points scored, etc., we can create 125 backward selection stats now to form the basis of our predictions. We then concatenate these statistics, which are stored in separate arrays, into one data frame. And now we can see the column names of the data frame reflect our 125 statistics. Now I'm going to pass it over to Dove to tell you about GLMNet, a regression package in R which we use to create our prediction.
Now we are going to use GLMNet, but what is GLMNet? GLMNet solves for a linear model that minimizes total error in predicting events subject to a regularization constraint, lambda, on how much fitting can be done. GLMNet optimizes between two types of regularization controlled by the alpha term. The output is the beta coefficients at different values of lambda. Linear regression gives predictive ability, while regularization and cross-validation prevent overfitting.
Now we apply our dataset to the GLMNet package. Using the function cvfit, GLMNet minimizes mean squared error by choosing the correct amount of coefficients. In this case, we choose to use roughly 26 of our 125 coefficients. Before looking at the accuracy and expected payout of our model, we first want to discuss our betting strategy. Our betting strategy is a series of if statements which can be represented by this flowchart. One of the main parts of this betting strategy is something we call a cushion, which is the difference between our spread and Vegas's spread. We can increase the cushion to be more conservative in our betting. If our spread chooses the same team to win as Vegas, and the difference between the two spreads is greater than or equal to the cushion, we will then choose to bet with or against Vegas depending on where our spread comes in compared to Vegas. Now, if our spread does not choose the same team to win as Vegas, the only thing that matters here is the cushion, because we already know we want to bet against Vegas. If the cushion is adequate, we will bet against Vegas, and if not, we will not bet. Before we look into our payout, it is important to understand the 11/10ths rule, which most bookkeepers adhere to. In this practice, for every $11 that a bettor bets, they will only receive $10 in winnings. In other words, if the bettor loses, they will lose 11/10ths times the amount they bet. Because of this, being right 50% of the time will not ensure that the bettor has a positive payout, but instead the bettor has to be right 52.4% of the time. Thus, for our model to have a positive payout, we want to ensure that we are beating the Vegas spread 52.4% of the time. Now, let's look at a scenario in which we bet $10 on 200 games in the 2015 season. We can see that the optimal cushion is one that is closest to 0. You can see the success of our model here, as betting $10 on 200 games results in a payout of over $1,000 with a cushion of 1. In this test scenario, our model was correct over the Vegas spread over 80% of the time, which is extremely exciting because of the potential payouts. We're really looking forward to the 2016 NFL season when we can apply this model to the betting markets.
Oh! That could go long. Let's go! Let's go! No, 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 no!